human, so either before the human step or after the human step, in a way that we can start to make some different claims about our metrics here. If these two systems are actually completely independent of each other, we actually see the error drop dramatically, right? Like we've gone from 2% to 0.1% error in that case. Now, if these systems are fully dependent and those errors are the same, well, we get no better than the 2% here. So we've kind of bounded it though in a case where the optimistic error looks a lot better. Hey, we got another algorithm on the team. This one it's still not even as good. It's only 90%. We were thinking we would just throw it away and not do anything with it. But hey, actually, this thing could still help us. We can apply it sequentially. It still has a 10% error rate, but the fact that we think it might be independent from some of our other errors and we can apply it sequentially, all of a sudden our best case error starts looking even better. Now our worst case hasn't changed at all here. And so it really starts questioning, all right, well, how do we make sure we're in this independent bucket here and not in this dependent bucket? Because if we can really establish that we have these different algorithms and different humans that are having errors independent of each other, the likelihood that those errors overlap starts to become very, very unlikely. And we start to feel really pretty good about the safety of our system. So here's kind of that best case that I'm describing, right? And this is kind of my Venn diagram of all error. Human has the least error, doesn't overlap at all with algorithm A, doesn't also overlap at all with algorithm B. Awesome, we've hit the super low error rate. We're very happy about that. Well, we could also have the worst case too, right? They overlap perfectly and they're all contained within that human error. Well, in that case, the computer vision algorithms truly didn't do anything. But we can actually, we don't have to like just theorize about this. We can actually compute this as long as we have some ground truth available to us. We often think of metrics in terms of precision recall. Oftentimes we don't go the next level deeper with our metrics to say, hey, let's look at specific examples and categorize them into buckets. And say, hey, here's the ones the human got wrong. Here's the ones algorithm A got wrong. And we can actually measure how independent these different systems are. And if we can establish, based on some blind ground truth, that the human got those wrong, algorithm got these wrong, and they're independent enough, we can actually start to make some claims like this about our error. That's super exciting, actually. And it also gives that person who, algorithm B designer, who's like, oh, I was only at 90%. It's like, hey, you're still helping. Actually, you brought our error down significantly. The reality is actually likely something more like this, right? There's a little bit of overlap, hopefully not entirely overlapped. So we're somehow bounding the error in this area. But I think this is actually a really important aspect of mapping when you think of it in terms of safety, is being able to establish how safe are we and where can these different algorithms contribute to that safety. So I'm kind of making a statement here. Computer vision models, they don't need to be 100% accurate to have value. But they need to be somewhat independent in order to improve our safety. And hopefully that makes sense now based on the little statistical exercise we did. So the question becomes, what can we do to achieve this independence? How can we come up with more computer vision algorithms that make things more independent from each other such that we drive that error rate down and down? So I propose some different ideas here. One is to combine different techniques together. You can sort of think of this as like ensemble a little bit, but I'm actually thinking of it at a more system level, where you may have some models, so again, we're using the stop sign example here, that have been trained just as a box detector. So it's essentially a YOLO-like approach. We know the advantages of those sort of approaches are they're good with big objects, and they've been trained on a particular set of bounding box label data. At the same time, we may have a segmentation, and this is one from Raquel's team as well. We may have a segmentation-based approach that's looking at pixel-wise segmentations. It's super accurate. It was trained on a different set of labels as well, because it's trained on pixel-wise labels. And the characterization of the false positives start to look a little bit different between those two systems. And then the third is we've trained sort of a whole image. I call it a distance estimator. It's essentially, we use map data to say we know we're coming up upon a stop sign, look at the whole image and figure out how far we are from that stop sign. So we don't actually know what features it's picking up on, but we imagine it's looking at different things than just the stop sign. It's looking at the context, the fact that I'm approaching an intersection, the fact that I'm seeing some other features around me that make this look like a stop sign. It starts to feel like a very independent type of system than a pixel-wise segmenter or a box detector. And combining these different things together is a great idea. Other things you can do, this is getting a little bit more basic. You can split training data for independence, so I'm sure we all do this already. Split data geospatially, do day-night splits, do camera splits. You can leverage multiple sensor types on the car as well. So my team's heavily focused on camera-based approaches, but you can also use LiDAR as a way to generate some sort of independence as well. You can use radar. This is our older self-driving car. Raquel revealed the newer one to y'all this morning. But by gaining independence from different sensors, they have different failure cases, again, that hopefully don't overlap. And then the final point I'd like to make here, this is sort of a cute graphic someone on my team made, but we can guarantee safety by keeping humans in the loop until the robots are actually ready to take over, or until the automation is ready to truly take over. And I think this has actually been a theme of our workshop today, is everyone saying humans are important to building maps, and I'm saying the same thing here, actually. So.